Hello everyone, and in this video, I'm going to be discussing a really cool geometry concept called homothety. And it ends up being really powerful inside olympiad geometry. Before I get into all of the nitty-gritty, I want to give a quick sneak peek of what it can do. So suppose we have a triangle ABC, and its incircle touches BC at D. And then we take the point X diametrically opposite D on the incircle. So dx is the diameter of the incircle here. Then if we draw the line AX and let it intersect at E, then it turns out that BD is equal to CE. These two lengths here are equal. And we're going to be using homothety to prove this later on in the video. So without further ado, let's get going. What is homothety? So suppose we have a point O here, and we have points A and B here. Here's A. And what a homothety does, it just scales the lengths, the distances from A and B. So we have that OA can map to OA prime with the homothety, and then OB can be mapped to OB prime with the homothety. So B prime. Rigorously, it's a function H that takes A to A prime and B to B prime, where OA prime over OA is equal to K, where K is a real number. Now you might see something from this diagram that seems a bit off. It's that AB is parallel to AB prime, A prime, B prime. So these two lines are parallel. Why would this be the case? Well, this directly follows from some similarity laws called SAS similarity. These two angles are the same, they share a common angle. And from this homothety, we have that the sides also have an angle relationship. So these triangles are similar, OAB and OA prime B prime, which means that these two angles here are equal, implying that they're parallel. Also, if C is a point on this line, AB, and then we draw OC to intersect A prime, B prime at a point C prime, then it turns out that H of C is equal to C prime. Because it also follows from the similar triangles. Because these triangles end up being similar because of the parallel lines, OCB and OC prime B prime, implying that OC over OC prime is equal to OB over OB prime, which ends up being 1 over K. And also, BC over CA is equal to B prime C prime over C prime A prime, because BC over B prime C prime is equal to OC over OC prime, which ends up being CA over CA prime, because this triangle and this triangle are similar, and this triangle and this triangle here are similar. Long story short, homothety scales lengths, but preserves angles and parallel lines. A commonly used example of this is, suppose we have a triangles A, B, and C. And then we have more triangles A prime, B prime, and C prime. And we have that AC is parallel to A prime, C prime. CB is parallel to B prime, C prime. And BA is parallel to A prime, B prime. So these two lengths are parallel, these two lengths are parallel, and these two lengths are parallel. Then A prime, B prime, and C prime intersect at the same point, P. Now, how do we go about proving this? So let P prime be the intersection of B prime and C prime. And we want to show that P prime lies on line AA prime. So we know that it maps BC to BC prime. So P prime is the center of homothety mapping B to C, B to B prime, I meant, and C to C prime. So it maps this segment here to this segment here. However, since we have the same angle here, here, and here, and the same ratio of lengths by similar triangles, we have that P maps A to A prime as well. So that means that P must lie on AA prime, as we needed. Now we're going to go ahead and take a quick look at some examples that take use of homothety. Now we return back to the example that we presented at the beginning. So we have this triangle ABC and the tangency point to the incircle, which ends up being D. And then we have the point diametrically across, which is X. And we want to prove that the intersection of line AX with BC, the point E, satisfies that BD is equal to CE. Now you guys might know, some of you might know, and I won't go ahead and prove this here, but it turns out that this thing called the X circle, which is tangent to BC and tangent to the extensions of the sides of AB and AC, ends up intersecting at a point E, ends up intersecting BC at a point E prime, such that BD is equal to CE prime. So really all we have to do is prove that A, X, and E prime are collinear, where E is the tangency point of this X circle. So prove that A, X, and E prime are collinear. So how can we go about that? Well, we know that collinear points usually work well with homothety, and we have like a circle here and a circle here. So we can try connecting the line from AX to AE. There we go. And then we can also draw the tangent, because E is the tangency point of the X circle to the triangle. So might as well make X the tangency point of an X circle to something. So we draw the tangent to this incircle at X. And it intersects B prime and C prime. And if we can show that B prime C prime is parallel to BC, then we're set. So how can we do this? Well, since XD is the diameter, we know that XD is perpendicular to BC because I lies on this line segment where I is the end center. So this angle is a right angle. However, since IX is also a radius and B prime C prime is tangent, this angle is also 90 degrees. So we end up getting B prime C prime is parallel to BC as we need. And then we have that a homothety maps ABC prime C prime to ABC. And since X and E have the same definitions with respect to each triangle, X circle tangency point and X circle tangency point, we have H of X is equal to E prime. So that means that A, X, and E prime are collinear, since A is the center of homothety. And since E prime satisfies that BD equals CE prime, we can actually get rid of the X circle from the picture. And then we can say that if this is the intersection, E, then BD equals CE, as we need. Now we're going to go ahead and take a look at another example. So now we have a triangle ABC, and we have its incircle, which touches the side BC at D, and it has incenter I. And again, we have X as a point diametrically opposite D, and AX intersects line BC at E. And also AS here is an altitude, and we let IE intersect AS at M. Now, it turns out, and we're going to go ahead and prove this in a minute, that AM is equal to MS. And we're going to go ahead and prove this using homothety. So let's get started. So we also have this angle here as a right angle. So we have that line AS is parallel to XD. So that means that triangle EXD and triangle EAS are similar. And stronger than that, they're actually homothetic. So there exists a homothety H that maps EXD to EAS. And since EI meets AS at M, we know that from what we said earlier, that H of I is equal to M. However, we know that DI over IX is equal to SM over MA because of the properties of homothety. However, we know that DI over IX end up being 1 because they're both radii of the incircle. So end up being 1. So AM equals MS. This is a really astonishing result if you think about it. And you might think it's like, how the heck do I prove this in the first place? But homothety essentially like trivializes it in a way, given the diameter of the incircle configuration. And we can actually rephrase this in a different way. If we have an X circle here, and then we have some X circle here, and it's tangent to BC at the point E, then EI, where I is the center of the incircle, intersects the altitude at its midpoint. So we can actually eliminate the diameter of the incircle entirely from this problem. We can get rid of X. So tangency point of the X circle and the incenter meet the altitude at its midpoint. And now it turns out that the center of this X circle here, IA, and then IAD also meets at the midpoint of the altitude. I won't go ahead and prove this here, but it's a simple enough exercise that you guys can do. It's essentially like completing this incircle here. This X circle I meant, sorry. And then we have AD. And then it actually meets at the bottom point of the X circle. Suppose that this is a point X. And then like the bottom point. And it can also be proven with the homothety from this triangle from this circle to this huge circle here. And what the key thing to realize is that AS is parallel to EX, so that DAS and DXE are homothetic. And since M is the midpoint of AS and EX and IA is the midpoint of EX, then MIA passes through D. So that means that IAD and IE intersect at the point M, which is the midpoint of the altitude. This is a really cool result. And we're going to go ahead and take a look at another example, or one final example, that will wrap this all up. And it ends up being, and I think this is one of the best examples that I'll present in the video. So here's a final example that I'll present in this video. So once again, we have a triangle ABC, and the incircle touches side BC, CA, and AB at D, E, and F. And I is the incenter. And then we let DI and EF intersect at a point X. And then we let AX intersect BC at a point M. The key claim that we're going to make here is that BM is equal to CM. In other words, AX is just the median of the triangle. So how could we go about proving this? Well, we not really know much about like BC that much, or CM on that matter. So I feel like we should just keep things in the realm of X. Why not? So if we want to map M to X, mapping makes us think of homothety. So we can end up like drawing a parallel line here through X. There we go. And it intersects at B prime and then C prime. So now we know by definition, and the reason why we constructed it in the first place, that h of a b prime c prime is equal to abc, which means that h of x is equal to m. So if we can actually prove that b prime x is equal to xc prime, then this would automatically imply it's actually equivalent to bm equaling mc. So now we've actually gotten rid of the point m from the problem entirely. And now we just wish to show that b prime x is equal to c prime x. So how would we go about this? Well, first of all, suppose that this were true. Suppose that b prime x was equal to x c prime. Then we have this right angle here because of the parallel lines, because this angle here is a right angle as well. So we know that dx is a perpendicular bisector of b prime c prime. So since I also lies on this perpendicular bisector, so this would mean that b prime I is equal to I prime c. No, IC prime. So that means that b prime x is equal to xc prime is equivalent to b prime I is equal to IC prime. Because then di would be the perpendicular bisector. So how do we go about proving this? Well, we know that AI is an angle bisector, and if we have a circumcircle of triangle ABC, so we have the circumcircle of the triangle ABC. Sorry if this is a very, very bad looking circle, but the angle bisector of BAC intersects this circumcircle at a point x such that or a point y such that b prime y is equal to c prime y. However, we know that b prime I is equal to c prime I, so we just need to prove that I equals y. In other words, we want to just prove that ab prime ic prime is cyclic. So this is equivalent to saying that a b prime I c prime is cyclic. Now at this point we might feel kind of stuck because we don't really know that much about the points b prime and c prime either way. Well, the reason why we kind of want to do b prime and c prime in the first place is because we have right angles here and here at a right angle here. So f X and E are the perpendiculars from I to A B prime, B prime C prime, and C prime A. So let me go ahead and write this down. F, X, E are feet of the perpendiculars from I to B prime A, B prime C prime, and C prime A. And we know that all of these 3 points are all on the same line because X also lies on EF by definition. And I won't prove this here, and many of you might know this already, but there's this theorem called Simpson's line, which states that AB prime IC prime is cyclic if and only if F, X, E are collinear. In other words, all the feet of the altitudes lie on the same line, if and only if AB prime IC prime is cyclic. So therefore, we are done, because that means that B prime X equals XC prime. And then we can just take a homothety and then map it down here to M. And BM equals MC, as we need. So in conclusion, to summarize up the video, we discussed homothety, which is like dilates lengths. And then we gave a few examples that relate to the incircle and how packed it is. For example, we considered midpoint of altitudes. We also discussed the diameter of the incircle. And then finally, to top it off, we discussed the touch chord, and diameter concurrency with the median. So that's it for this video. Thank you so much for watching, and I'll see you in the next one.